Alright, silly people, here's the situation. We have a free particle with the initial wave function given by this, and we need to normalize it as well as find the time-dependent wave function corresponding to it and find a bunch of expectation values. So the whole 9 yards. So get your popcorn, buckle in your seats. This is going to be a long video. We have to take the integral of the square modulus of the time-independent wave function um, over space and set that equal to 1 to normalize it. So we got a squared minus infinity to infinity e to the minus 2ax squared dx is equal to 1. And then that integral is just the square root of pi over 2a. It's a Gaussian. And so we've got 1 on this side, and that is going to tell us that a is just 2a over pi to the 1/4. So we've got that going for us. We can rewrite now psi of x and 0 as 2a over pi to the 1/4 e to the minus ax squared. So we have the time-independent wave function. To get the time-dependent one, first we need to take a Fourier transform of the time-independent wave function. So we need to take the integral over all space times the e to the minus I kx psi x and 0 dx. So for us, that looks like 1 over square root 2 pi, and then there's a 2a over pi to the 1/4 there. And then the integral is just e to the minus I kx minus ax squared dx. And then Griffiths kind of suggests that we do a change of variables in order to do this integral by defining the variable y as being square root of a times x plus I k over 2a. And from that, dy is going to be just root a dx. So dx is dy over root a. And we can rewrite the integrand in a much sillier way, kind of just moving the 2 pi from the radical into the 1/4 by squaring the contents, and also getting a 1 over root a from changing the variable. We have the integral over all space of e to the minus y squared minus k squared over 4a dy. So continuing to simplify the stuff out front, I have an a over 2 pi thirds, and then I'm going to multiply by a squared on the bottom as well to deal with the radical. And then this integral is just e to the minus k squared over 4a times root pi. So we can even move that root pi in there. So we have 1 over, or actually pi squared over 2 pi thirds a to the 1/4 times e to the minus k squared over 4a, which is going to be 1 over 2 pi a to the 1/4 to the minus k squared over 4a. Glorious. So now we can actually construct psi of x into t, which is the inverse Fourier transform, pretty much. So it's minus infinity to infinity, our 5k, which we just found, times exp ikx minus ih bar k squared over 2m times t, and you integrate that over k. So for us, that looks like 1 over root 2 pi. We have the 1 over 2 pi a to the 1/4 thing. And then we have the integral of a bunch of exponents. We have ikx minus ih bar k squared t over 2m minus k squared over 4a dk. And I'm going to regroup it in a way that's a little bit more suggestive. So, and also move the radical into that 1/4. So it's going to be 2 squared pi squared 2 pi a all to the 1/4. And then the integral, we're going to split it up into things which depend on minus k squared, which here look like ih bar over 2m times t plus 1 over 4a. And then we're going to get some stuff which depends on minus k, and then we have minus ix in there. And that's what we are integrating. So this is an integral of the same form that we just did, except now it's k rather than x. So we can make like a similar transformation of variables, where now I'm going to define y as being the square root of ih bar over 2m t plus 1 over 4a times k minus ix over ih bar t over m plus 1 over 2a. This is like an identical unit transformation here. But we're going to massage it a little bit just to make it look nicer. So factoring out a root 4a from the radical, I have that this now looks like 2ih bar at over m plus 1. Okay. And truly there should be a 2 here, and that now the math makes sense to me. But then also in here we want to multiply this fraction by 2a on the top and the bottom, so we'll have 2aix over 2ih bar at over m plus 1, right? And this is where a quantity that Griffiths defined will come in useful, because he said that gamma is defined as the square root of 1 plus 2ih bar at over m. So what we have here are a couple different things which depend on gamma. In blue, 1 over root 4a, and then this is a factor of gamma, and this is k minus 2aix over gamma squared. And we can very quickly take the derivative of this, so dy will be gamma over root 4a dk, and we can quickly just say that dk is now just root 4a over gamma dy. And we can actually rewrite our integral now in a way that's nice. So In the 1/4 thing, now we just have 2/3 pi thirds a, so 1/4, and then we multiply by our change of variable thing, and also we now have the integral from minus infinity to infinity of e to the minus y squared dy, and then also see an additional exponent, which is minus x squared a over gamma squared. So we're just going to move the root 4a into that 1/4. So we're going to say 2 to the 4th a squared over 2 to the thirds pi to the thirds a 1/4. We still have 1 over gamma here. And now this is going to be the square root of pi, that integral. And I'm just going to write this now as ax squared over gamma squared here. We can simplify the stuff that's in here even more. So we'll have a total 2a over pi thirds, and then multiply by an additional factor of pi squared from the root pi thing. And that's also the 1/4. Then we have 1 over gamma e to the minus ax squared over gamma squared. So all in all, it's just 2a over pi to the 1/4 solid. And this is going to be 1 over gamma, and this is going to be e to the minus ax squared over gamma squared. Okay. Now we need to find out what the square modulus of the wave function is and express it in a certain quantity. So just taking the square modulus of this junk, we'll have the square root 2a over pi 1 over, now gamma is a complex variable, so this is going to be the mod squared of that down there. And then you'll have e to the minus ax squared over gamma squared, but also e to the minus ax squared over gamma star squared, because again, it's all complex. 2a over pi 1 over gamma squared. We're going to first of all multiply this thing by the complex conjugate of gamma squared minus, and there's not a 2 here, it's just minus ax squared. I'm just combining the two fractions together. This will be multiplied by gamma squared, and this is going to be the square of the square modulus, so mod 4th. Okay. So Griffiths actually gives us another definition that he wants us to put this equation into. He's pretty much saying that there's a w that can be thought of as the square root of a over the square modulus of gamma. So I'm going to start using that because we have a root a, we have a over gamma squared over here, so this is root 2 over pi times w times exp, and I do have to actually expand the definition of gamma for these parts. So gamma star squared looks like, just looking back at this equation up here, 1 minus 2i h bar at over m. and then minus ax squared, and now gamma squared is 1 plus 2I h bar at over m. And all of that, I'm just going to have it be divided by mod gamma to the fourth. So we got the 2 over pi, we got the w, we got the exp. This term will cancel out this term, fortunately. So we just have minus 2ax squared over mod fourth gamma, which we can conveniently write as w e to the minus 2x squared w squared. And that's pretty nice. So we actually have to sketch this now. So I have this Desmos plot here of the square modulus of the wave function in purple. So in the limiting cases where t goes to 0, then w just looks like the square root of a, and so that's what I've written here. And as you can see, initially it's a pretty well-defined little Gaussian wave packet, so we can do a lot of stuff with this. But if you let t go to infinity, now you let w become really, really small. So I'm going to instead write 0.1 and then go smaller and smaller and smaller. And now it's basically just a straight line at 0. So when you let t go to infinity, your wave packet is actually dispersing over all space, and so you just have no idea where the particle is or how to get any information out of it. It's completely useless. But we're not actually done with the problem yet. We also have to calculate a bunch of expectation values for this particle. Namely, first we need to do the expectation value of position, which, as usual, is just the complex conjugate of psi times x times psi. But since the wave functions will commute with x, you can just think of this as x times mod squared of psi. So we've got minus infinity to infinity. We've got x times the square root of 2 over pi times w e to the minus 2x squared w squared dx. And I'll tell you this is 0 because you've got x times e to the minus x squared, which is always 0, which means we get the expectation value of momentum for free by Ironfest theorem, also 0. But then now we need x squared, p squared. X squared can just be from minus infinity to infinity root 2 over pi w x squared e to the minus 2x squared w squared dx. And I'm going to make a u substitution. So I'm going to say that u squared equals 2x squared w squared. And so u is just square root 2xw. So du is just root 2w dx. And make, just put those in there. So now we have that x squared will be root 2 over pi w 1 over w root 2 1 over 2w squared, integral from minus infinity to infinity, u squared e to the minus u squared du. Alright, this root 2 will cancel out this one, so now we just have, and then this w will cancel out this w, so we have 1 over 2 root pi w squared integral, and then that integral is actually just root pi over 2. So we have 1 over, let me actually write pi there, because it's root pi over 2. So we have 1 over 4 w squared for the expectation value of x squared. That's lovely. Now we need to do p squared, and this is the suckiest part of this problem, I'll say that. Because expanding the definition of the momentum operator and also of psi, not psi star, I'm just expanding psi, of 2a over pi to the 1/4 times 1 over gamma e to the minus ax squared over gamma squared dx. So we can actually move out a couple of constants. There's going to be a gamma down here. There's going to be a 2a over pi to the 1/4 here. This is going to be minus infinity to infinity, psi star, and then we'll actually do the first derivative, which is going to look like minus 2ax over gamma squared e to the minus ax squared over gamma squared dx. And then we're going to factor out some more constants. So now it's going to be 2a bar squared over gamma to the 3rd. We got 2a over pi to the 1/4 here, minus infinity to infinity, psi star. And now we'll go ahead and do the other derivative, which is going to be minus 2ax squared over gamma squared e to the minus ax squared over gamma squared plus e to the minus ax squared over gamma squared. Okay, now the reason I've done this really strange way is because I actually want to recombine this stuff now into integrals of the mod squared of psi. So we have just the integral of psi star e to the minus ax squared over gamma squared dx minus 2a over gamma squared integral psi star x squared e to the minus ax squared over gamma squared dx minus infinity to infinity. By killing a factor of gamma in this denominator, so it's just gamma squared down here, and by getting rid of the 1/4 thing, we will have an integral of the mod squared of psi minus 2a over gamma squared integral of x squared mod squared psi dx. And both of those integrals we've actually done before. Well, actually, we haven't done the first one. But that's okay. We're just going to use our definition of mod squared psi now with the overall factor of 2 pi w out front. We'll have an integral of e to the minus 2x squared w squared dx minus 2a over gamma squared integral x squared e to the minus 2a w's, nope, 2x squared w squared dx. And I'm going to use the same u sub as before that I did for my other mod squared psi integral. That being that we're going to end up with a factor of 1 over root 2w. And this is going to be minus u squared du. And then we'll also have a 1 over root 2w here, and then also 1 over 2w squared times the integral u squared e to the minus u squared du from minus infinity to infinity. We'll factor out root 2w down there, which will just end up canceling this root 2 and this w, and then try to simplify a bit more to a h bar squared over gamma squared. We still have the 1 over root pi, but now this integral is just root pi. This 2 will have canceled out this 2, so we just get a over gamma squared w squared, and then that integral is root pi over 2. So we can also factor out a root pi from everything and have 2a h bar squared over gamma squared 1 minus a over gamma or 2 gamma squared w squared. And then a lot of this now is just going to be algebra, because I'm going to prove that this quantity that I'm writing out right now is just going to end up being 1. So it's going to be a over gamma squared w, or gamma fourth w squared. So just multiplying everything, this thing by gamma squared w squared on top and bottom, and then it's a minus a, just to give them the same denominator, like that. And then remembering our definition of w as being just the square root of a over mod gamma squared, we'll have 2 gamma squared a over mod gamma to the 4th minus a, and then that denominator becomes gamma to the 4th a over mod gamma to the 4th. Okay, so in that first set of square brackets, we're going to combine these into the same fraction again, and we'll have gamma 4th here, and then in the second square brackets I'm going to invert it, so it'll be mod gamma 4th over gamma 4th a. Now we can cancel this out with this and also cancel out all these a's to get the expression that we will actually expand to gamma squared minus mod gamma 4th over gamma 4th. Now, why is this equal to 1? So gamma, as defined a long time ago, was just the square root of 1 plus 2i h bar at over m. So we have 2 times 1 plus 2i h bar at over m and we have minus mod gamma fourth ends up being 1 plus 2h bar at over m squared. And then gamma to the fourth ends up being 1 plus 2 ih bar at over m squared. Right? So we're going to expand some squares. So we'll have 2 plus 4 ih bar at over m minus 1 minus 4h bar squared a squared t squared over m squared. And on the bottom, it's going to be 1 plus 4 ih bar at over m plus, or actually now minus 4h bar squared a squared t squared over m squared. And you can see that this 2 is going to be subtracted by 1. So we're actually going to have the same thing on top as we do on bottom. So everything will cancel out, and we just get h bar squared a, which is the answer that Griffiths got as well. Finally, we can get sigma x and sigma p. So sigma x will be the square root of whatever we got for the expectation value of x squared, which is 1 over 4w squared, which we can write as 1 over 2w. Sigma p will be the square root of h bar squared a, which we can just write as h bar root a. And then sigma x, sigma p will be 1 over 2w h bar root a. And we'll expand the definition of w actually as being 1 plus, nope, it's the square root of 1 plus 2 h bar at over m squared over a. And then that a cancels out here, so we just have h bar over 2 square root 1 plus 2h bar at over m squared. Now, to get it closest to h bar over 2, you just set t equal to 0. Then you find that sigma x, sigma p will go to just h bar over 2. But once you let t become really large, then the uncertainty becomes larger and larger. And so the uncertainty principle is satisfied. All right.